All right. Hello, everyone. Welcome to our Week 10 lecture in real analysis. This week, we're going to be talking about functional limits, some of their properties, and we're going to do a few examples with continuity. We're going to use the formal definition of continuity to prove some functions are continuous at points. Okay. So, the idea of functional limits is very similar to the definition, or I should say the definition for functional limits is similar to the definition for limits of sequences. So I want to recall that definition, and hopefully by now you know this one really, really well, because this was the one where you were supposed to brew a pot of coffee and think about it for a long time. So hopefully that's, in your head, solid. So let's just review what this definition says. Okay, so a sequence converges to a limit L if for every epsilon bigger than 0, there exists some n in the natural numbers, so that when you go along far enough in your sequence, aka little n is bigger than capital N, this implies that you stay in your epsilon neighborhood. So that an minus your limit L, the distance between those guys is going to be less than epsilon. Okay, and so, we have this picture right here. So we have our sequence A sub n is plotted on the y-axis, and whatever little n you're at is plotted on the x-axis. And so we said that, if our limit is L, then after some capital N, all of the terms should be trapped within this epsilon neighborhood. And remember, the epsilon neighborhood is anything between L minus epsilon and L plus epsilon. Okay, so we can see that from our picture here, we do have that the sequence is going to converge because after capital N, all of these terms are going to stay in that neighborhood. So with that being said, let's get to limits of functions. And so the idea here, it's going to be slightly different from sequences, but not completely different. The idea is pretty similar. And what we're trying to state formally is, what does it mean when x gets close to a number, then f of x gets close to a number? What does that mean formally? And you can see kind of on the picture what's happening here. Now, we don't care with limits. Remember from Calc 1, Calc 2, and so forth, we do not care if the function is even defined at what we're claiming to be the limit. Okay, we don't care that it's defined or not. But what's important is when x gets really close to that number, f of x is going to get close to the limit, whatever we're calling the limit. And so, one way of looking at that in the picture is if your x is in this delta neighborhood of C, well, that implies that f of x is going to be in this epsilon neighborhood of L. Okay, so let's go ahead and formally define this. Okay, so if we have a function from a set A to R, and we're going to let C be a limit point of A. Okay, now C, as I mentioned before, we don't care that the function is defined at C. We don't care about that at all with limits. But we should have that it is a limit point of our set A. Okay, then we say the limit as x approaches C of f of x equals L if for all positive epsilon there exists some delta, so that when x is in that delta neighborhood, okay, when the distance from x and C is less than delta. Okay, notice that we have a greater than 0 and not a greater than or equal to 0, because if we have greater than or equal to 0, that implies that x equals C, and we don't care about what happens when x equals C. We only care about what happens around x equals C. Okay, so whenever this happens, whenever the absolute value of x minus c is less than delta, this implies that the distance between f of x and our limit L is less than epsilon. So whenever, you should think of it like this in your head. Whenever x is in the delta neighborhood of c, f of x is in the epsilon neighborhood of L. And okay, so we say that the limit as x approaches c of f of x converges to L. Okay, so we can see what's going on formally here in the picture. I give you an epsilon. Okay, I give you a neighborhood. That's what you're given. You cannot control this. You are given any epsilon neighborhood, and your job is to find a suitable delta neighborhood so that whenever x is in this delta neighborhood, f of x belongs in this epsilon neighborhood. Okay, so the big idea here is that you cannot control epsilon. Okay, epsilon is given to you. You can control delta. And what we're going to find is that the delta that we pick is going to typically depend on the epsilon that we're given. And it can only depend on the epsilon that we're given. So maybe to illustrate limits, we can look at an example where the limit doesn't exist. So if you look at this picture to the left, I have a piecewise function, and so there's a jump discontinuity at x equals 1. And we want to claim, using the formal definition, that the limit of the function doesn't exist when x approaches 1. And so the intuition here is that I'm going to give you an epsilon neighborhood for which you cannot find a delta neighborhood that satisfies the definition of a limit. And so I can give you an epsilon neighborhood so that no matter how small you make your delta neighborhood around centered at 1, I'm going to be able to find an x in that neighborhood so that the distance between our limit and f of x is going to be outside of the epsilon neighborhood. So let's look at what that means on the picture. So I have drawn my limit, and I drew it at L equals 0, but you can apply the same logic to show that no limit is going to exist. And the epsilon neighborhood that I've drawn is in the red dashed lines. And so I give you this epsilon neighborhood, and you're tasked with finding a delta neighborhood around 1, centered at 1, so that for any x in that delta neighborhood, this implies that f of x is going to be in that epsilon neighborhood. But we can see that this is not going to ever work, because if no matter how small I make my little delta neighborhood, so here's my delta neighborhood, and so I can see that there's a little x somewhere in there. There's a little x guy. And so that would correspond to f of x being, I don't know, like right here. Okay, and we can see that the definition immediately it's gonna fall through, right? Because what do we have here is we have a delta neighborhood, and we can make it arbitrarily small, centered at 1. And I can give you an x in that delta neighborhood so that f of x is bigger than the distance between f of x and L. Okay, so that's going to be this distance right here. So this distance is going to be greater than or equal to epsilon, right? It's not in this neighborhood. And that's the idea. That's the intuition here. Okay, so what does this mean formally, that the limit doesn't exist when x approaches 1? Well, formally, this says that there's some epsilon bigger than 0, i.e. some epsilon neighborhood, so that for any delta neighborhood, okay, so for any delta bigger than 0, no matter how tiny I make my delta, there is some x in that hood, in that neighborhood, okay, some x in that neighborhood, and that's written here with absolute value bars, that the distance between x minus 1 is less than delta. That's just saying x is in this delta neighborhood centered at 1, for which the distance between f of x and the limit is going to be bigger than or equal to epsilon. So that, f of x minus the limit is not in the epsilon neighborhood. Okay? So, now that that's out the way, let's do some proofs. And I think these are kind of fun. Okay, I'm just going to come out and say it. I think these are kind of fun. If you think they're fun too, don't be ashamed, okay? Because there are other people that feel this. So, the idea here is to do the same sort of scratch work that we did for limits of sequences. Okay? And so we want to go back to our definition. We want to show, and I'm gonna be not sloppy, but I'm not gonna say, x minus 3 has to be bigger than 0, less than delta. I'm gonna shorten this and just say x minus 3 less than delta, and we're just gonna live with it and just assume, okay, yeah, absolute value of x minus 3 can't be 0, x can't be 3. Okay, fine. So what we want to show, and this is my scratch work, we want to show from the definition that given an epsilon bigger than 0, we need to find a delta. Okay, this is what we're trying to find, such that, what's our C? Our C here is 3, okay? We're getting close to 3, and we want to show that the limit of the function is 17. Okay, so this is our L, and this is our C in the definition. Okay, so we want to show that distance between x and 3 being less than epsilon, so if x is in the, sometimes I say epsilon and I mean delta. I'm sorry about that. I mean delta. So if x minus 3 is less than delta, so if x is in the delta neighborhood centered at 3, that means that f of x minus my limit, well, I'm claiming that my limit is 17, is going to be less than epsilon. So this is what I'm trying to show. Okay, and so just like with the limits of sequences, you want to start backwards from here to figure out what your delta needs to be. Just like that's what we did to figure out what our capital N needed to be. It's the same kind of idea here. Okay, so this is still scratch work. F of x minus 17 less than epsilon. Now, f of x is 5x plus 2, so let's just go ahead and plug it in. Less than 17, less than epsilon. Okay, and we can simplify this, so let's see. Am I doing this right? Yeah. Okay, yeah. Sorry, sometimes I can't do mental math. I don't know about you guys, but I was just in my head like, yeah, negative 17 plus 2 is definitely 16. And then I was like, no, how could it be 16? Because then I can't pull anything out. Okay, so whatever. Sorry, I'm going off on tangents today. So 2 minus 17 is going to be negative 15 less than epsilon. And from here you can pull out a 5 and you get x minus 3 less than epsilon. And if the point is I'm trying to see if I can find whatever is less than delta in here somewhere so that I can know what to choose for delta. Okay, so like I see an x minus 3, and that's awesome. If I divide both sides by 5, I get x minus 3 is less than epsilon over 5. And I see that based on what I have here, I should choose my delta to be epsilon over 5, and then everything works out. Okay, so that's the idea here. All right, so this was just the scratch work. Let's do the formal proof. So the formal proof is we always are given an epsilon. Okay, so the epsilon delta challenge. You give me an epsilon, I find you a delta, and I just found it. Okay, and as I mentioned before, your delta is going to depend on epsilon usually. It's not going to, and it's certainly not going to depend on anything else other than epsilon. Okay, and we'll illustrate what this kind of means in the next slide, like intuitively, basically it's just like, okay, so I give you a really small epsilon neighborhood. So in order to respond to that challenge, you need to give me a super small delta neighborhood. So for everything to work out. Okay, so here's the proof. Let epsilon be bigger than 0, and this is where we have control. We choose delta. Choose delta equals epsilon over 5. Okay, and what are we trying to show? We're trying to show that this thing less than delta is going to imply this. Okay? So then we start with our hypothesis. X minus 3 less than delta implies, well, we just chose delta. So let's plug it in. This implies x minus 3 is less than epsilon over 5. Then by the backwards scratch work, which I'm not going to write all of these steps, but by the scratch work above, this implies (5x). Well, maybe I will write it all out, okay? Let's just see what the logic is. I just want you guys to see this a few times. So, all right, so this implies, so since we're starting here, okay, so we have thus x minus 3 less than epsilon over 5 implies, okay, so then we just go to the next step backwards. 5 times x minus 3 is less than epsilon, implies, just distribute, 5x minus 15 is less than epsilon. Okay, and then, just skipping the second step and going to the first, f of x minus 17 is less than epsilon. And therefore, the limit as x approaches 3 of, what is it? 5x plus 2 equals 17. Okay, so we've just proved using the epsilon delta definition of a limit that the limit is 17. And we know this from calculus. 5 times 3 plus 2. Hello, like 17. Yeah, we got it. So let's think about what this means on a deeper kind of level here. Okay, with the definition. So again, we have this challenge. We're given an epsilon. You give me an epsilon, I produce a delta. Okay? And so I said this delta is going to depend on the epsilon you give me. All right? And so then when x is in this neighborhood, what is that noise? When x is in this neighborhood centered at 3, when x is in this delta neighborhood, that's going to imply that f of x is in this epsilon neighborhood centered at our limit, which is 17. So I have a picture here. And so let's just do some epsilon delta challenges so we can see what's going on here. so it's not as abstract, I guess. So I'm going to give you an epsilon equals 1. And so you're going to choose, based on the proof that we just did, you're going to choose epsilon over 5, which in our non-abstract case here is 1 over 5. Okay, and so then what I should have is that x being in this delta neighborhood, which is 3 minus 1 over 5, 3 plus 1 over 5, which is 2.8 to 3.2. Then this should imply that my f of x, okay, so if I apply f to any of these x's in here, this should imply that f of x is in the neighborhood L minus epsilon, L plus epsilon, which happens to be 16, 18. Okay, so we have a pretty, like a, relatively speaking, a fairly large epsilon neighborhood. And so I don't need my delta neighborhood to be super big to ensure that my f of x values are going to fall in between 17 minus epsilon, 17 plus epsilon. Okay? If I give you something smaller, so here's the next challenge. I'm going to give you epsilon equals 1 over 1,000. So by our proof, that means I'm going to choose delta to be epsilon over 5, which is 1 over 5,000. So now, in response to my challenge here, I'm giving you a smaller epsilon neighborhood than before. And I'm saying, okay, what does my delta neighborhood have to be so that all of these values, it's, if I were to choose the same delta neighborhood, I would have some values that are outside of what I want here. They're not going to all fall in this epsilon neighborhood. So in response to the challenge, epsilon equals 1,000, I'm going to choose delta equals epsilon over 5, which is 1 over 5,000. And so this is always going to imply that when x is in this neighborhood, I'm going to have f of x in this neighborhood. Okay, so again, the smaller the epsilon is, the smaller you need to make your delta. Yeah. And here's the big idea. The big idea is that, this is really a big point here, that the epsilon you should choose should only depend, the delta you choose should only depend on epsilon. There should be no other dependencies. Okay? So let's do another example here. So this time I have a function from the reals without 2, and the reason is because if I put in 2, it's going to be 0 here. Okay? And I'm going to define my function as 3x squared minus 12 times x minus 2. Okay, so let me look at my notes here, make sure I haven't been looking at them. So that's okay. Oh, yeah. What did I? Yeah, there's a typo in the notes that I wanted to mention here. I think I put in the notes that f of x was between 17 minus 1 over 5,000 and 17 plus 1 over 5,000, but it should be 1,000. Okay. All right. So let's go ahead and prove that the limit of this function is 12. And so, again, we want to do our scratch work. So our scratch work is, we're trying to figure out what delta needs to be, what I can choose delta to be. So the scratch work, we want, here our C is 2 and here our L is 12. And so from the definition, we want x minus 2 less than delta to imply that my function minus 12 over x minus 2 minus 12 is going to be less than epsilon. Okay, so that's what I want. And so I'm starting here to see what, if I can find an x minus 2. Like when I start simplifying, if I can find an x minus 2, and that's going to tell me what my delta needs to be. So let's go ahead and simplify this. We have 3x squared minus 12 over x minus 2 minus 12 over 1. This is going to equal 3x squared minus 12 times x minus 2 all over x minus 2. And cleaning it up further, cleaning it up further, we have that this is going to equal 3x squared minus 12x plus 12 over x minus 2. Okay, and so if I factor out a 3, this is going to be 3x squared minus 4x plus 4 over x minus 2. Factoring the top gives me 3 times x minus 2 all over x minus 2. And we see that these guys are going to cancel. And so I can pull out the 3 and leave the x minus 2 on top in parentheses. And we want this, again, I haven't been writing the less than epsilon at each stage, but we want this to be less than epsilon. And if I divide both sides by 3 to just get the variable term, I get absolute x minus 2 is less than epsilon over 3. And if I scroll back up to up here, that's going to tell me what delta needs to be. I want x minus 2 to be less than delta. And so if this were delta, everything would work out. So that's what I'm going to do. I'm going to say we're going to let delta equal epsilon over 3, and then the result will follow. Okay? So let's go ahead and do that. And I'm going to kind of do this in a different style, I guess, but it's the same logic as the previous problem. Just maybe like different orders of steps. So let's see. Same idea though. Like, okay, so our proof, let epsilon bigger than 0 be given. And here's our control. We choose delta equal epsilon over 3. Then hypothesis, okay. Then x minus 2 less than delta is going to imply that x minus 2 is less than epsilon over 3. Okay, and we're trying to show that this then implies that this guy is less than epsilon. Okay? Thus, 3x squared minus 12 over x minus 2 minus 12. That's going to equal, by our scratch work, this is going to be 3x minus 2, x minus 2, x minus 2. Okay, canceling the x minus 2's, I get 3 on the outside, x minus 2. And we said this was less than epsilon over 3, so that means this is going to be less than 3 times epsilon over 3, which equals epsilon. Okay, and we're done. So I did the same thing that I did for the previous problem. I just, in the previous problem, I worked backwards, whereas here I just worked forwards. I mean, whichever way you want to do it is okay. But yeah, that's the idea. So we just proved that the limit as x approaches 2 of f of x is indeed equal to 12. All right. Let's do another example. So this one is, you have to think a little bit more, but it's not too bad. So let's go ahead and do the other steps that we did and see what happens. So here's our scratch. We want x minus, this time our c is 3. That's our approaching value. X is approaching 3. And we want this less than delta to imply that f of x, which is x squared, minus the limit, which is 9, we want this to be less than epsilon. Okay? And so before, we were just going to take this and see what delta needs to be, simplifying it and all of that. So if we do that, this is going to be equal, if I just use the difference of squares and factor it, this is just going to be x plus 3, x minus 3, where I skipped the step. This is just, remember, the very second week, I think we talked about properties of absolute values. If you have two things multiplied on the inside, you can pull them apart in the absolute value. So that's what I did here. And we want this less than epsilon. Now I see the x minus 3. So if I isolate x minus 3, I'm going to get x minus 3 is less than epsilon over x plus 3. But I don't want to choose delta equal to this because remember, delta does not depend on anything but epsilon. Okay, and we have this x in here. So that's a problem. Okay, so here's the problem. We can't choose delta equal epsilon over x plus 3 because delta can't depend on x. Okay, it can only depend on epsilon. So what are we going to do? Okay, so here's the little trick here. Let's see. So here's the trick. The trick is that we're going to choose an arbitrary delta. Like we're going to choose a number. And we're going to show that if you choose delta, that's going to tell you where x needs to live. And it's going to give us a bound on this x plus 3. So that our delta doesn't depend on x. Okay, but x depends on delta. Okay, x depends on delta, but delta doesn't depend on x. So that's going to be the trick, and we're going to use this trick quite often. So, really mull this over, maybe make another cup of coffee or a pot of coffee or whatever, tea. Yeah. So, okay, I hit a chord or something, so I had to add this into the video. Okay, so where I left off was saying that we can't choose this to be delta because delta can only depend on epsilon, it cannot depend on x. So we have to do a little sneaky trick, okay? And the sneaky trick is we're gonna first say, okay, what happens when I choose just a random number for delta to equal? This is just arbitrary. It doesn't matter, okay? But the idea is like, okay, if I choose a random number for a delta neighborhood, that's going to tell me where x lives. Okay, so let me repeat this. X depends on delta, but delta can never depend on x. Okay? X depends on delta. Whatever I choose my delta neighborhood to be around the around 3, well, that's going to depend on where, like, that's going to tell me where x needs to live and where it can't live. So just bear with me, because I know this is weird. I remember the first time I saw this, I was like, what are you talking about? Like, whatever. But I'm going to try to make I'm going to try to make this make sense. So just bear with me. So what happens if delta equals 1? Now, I just arbitrarily chose 1. I could have chose 1 over 2. I could have chose 1 over 100. I could have chosen 3,000. Doesn't matter. Okay, I'm just trying to see, where is x going to live when delta equals 1? Because that's going to give me a bound on this thing. I do not want the delta that I pick to depend on x at all. And that's what I'm trying to get at here. So, what happens if delta equals 1? And maybe I should write it a bit more carefully. Maybe I'll say, what happens to x plus 3 when delta equals 1? Because I'm trying to bound this thing so that it doesn't, so that, we have a delta that doesn't depend on x. I feel like I'm saying that 100,000 times, but just bear with me. Okay. So when delta equals 1, then this hypothesis is going to say that x minus 3 is going to be less than 1, right? Okay, and by properties of absolute value, that's going to tell me that x minus 3 is less than 1, but bigger than negative 1, which tells me if I add 3 to everybody that x is between 4 and 2. And again, I'm trying to bound x plus 3, absolute of that. So if I add 3, that's going to be between 5 and 7. And that tells me that by absolute value properties, like if I were to plot this on the number line, that's going to tell me that the absolute value of x plus 3 can't be more than 7. Okay, so that's the idea here. Now I have established a bound. And if that's true, then if I, go back to the scratch, I had x squared, what was it? Minus 9 is equal to x plus 3 times x minus 3. Again, we want this less than epsilon. And if we have this bound, then this gives me that this is less than 7 times x minus 3, just using that boxed part above. And if I want this less than epsilon, let me do it over here. If I want this less than epsilon, then dividing by 7, I get x minus 3 is less than epsilon over 7. And that is my hypothesis here. If x minus 3 is less than epsilon over 7, then this is going to work out. Okay, so I see what happens when delta equals 1. And so what I'm going to do is I'm going to choose the minimum of delta equals 1 and delta equals epsilon over 7. That way, both inequalities are true at the same time, and then the proof works out. Now, you did not have to choose delta equals 1 to begin with. Remember, this was an arbitrarily, completely random number that I picked because I wanted to bound x plus 3. I said, okay, if I can bound x plus 3, then I'm never going to have to deal with a delta that depends on x. Okay? So that was all scratch work. And so let's go ahead and do our actual proof. And you do have to think about this for a second. I mean, you should think about why everything I'm saying is true. So here's the actual proof. We're gonna let epsilon be bigger than 0 be given. Okay, and so then we're going to choose delta as the minimum of 1 and epsilon over 7. Notice that this is perfectly fine and reasonable because delta no longer depends on x, it only depends on epsilon. Okay, so choose this to be our minimum. Okay, so I'm going to erase this so that we can make more room. Everything's going to work out. It's going to be awesome. It's going to be super cool. Okay, so this was just this epsilon over 7 came from our scratch work, remember? Okay, what's our hypothesis? Then x minus 3 less than delta is going to imply that it's going to be less than 1 and epsilon over 7, right? Because delta is the minimum of 1 and epsilon over 7. So if 1 is the minimum, it's certainly going to be less than epsilon over 7, because epsilon over 7 is bigger than 1. So this is going to imply that x minus 3 is going to be less than 1, and I said epsilon minus 3. I meant x minus 3 is less than epsilon over 7. Thus, x minus 3 being less than 1 tells us that x minus 3 is between negative 1 and 1. And this tells us that x is between 2 and 4. And this tells us that x plus 3 is between 5 and 7. And so x plus 3 is going to be less than 7. I'll just box this right here. Therefore, remember, we're trying to show that this thing is less than epsilon. This thing equals x plus 3 times x minus 3. And we just said x plus 3 is less than 7. So this means that this is going to be less than 7 times x minus 3. And so we dealt with this inequality already, but now we deal with the other inequality that's true that tells us that x minus 3 is less than absolute x minus 3 is less than epsilon over 7. So this is going to be less than 7 times epsilon over 7, which equals epsilon. So therefore, the limit as x approaches 3 of x squared minus 9 is equal to, oh shoot, I meant x squared, is equal to 9. Okay, so we've just proved that this distance between x squared and 9 is going to be less than epsilon with the assumption that x minus 3 is less than delta. Okay, so again, if you want to play around with this, instead of the first step choosing delta equals 1, choose it to be 1 over 100 and see what you get, right? The logic is going to work out the same. But the point of doing that, again, was to find a bound for absolute value of x plus 3. Okay, so let's look at a theorem next. So this just says that, we've seen this before with sequences, but it's saying that the limit of a function is unique. Okay, so if a function has a limit, then it converges to at most one value. So let's do the proof. So we're going to, the idea here is we're going to suppose that the limit is equal to two things, and we're going to show that those two things have to be equal to each other. So we're going to suppose that the limit as x approaches c of f of x equals L1, and we're going to suppose that it's not unique. We're going to suppose that the limit is also equal to L2. Okay, and so we're going to let epsilon be bigger than 0. Then, by definition of the functional limit, since this converges to L1, there is some delta 1 bigger than 0, so that, okay, our c is just c here, so that x minus c being in the delta 1 neighborhood implies that f of x minus L1 is going to be less than epsilon over 2. We're just going to do the usual epsilon over 2 trick here. Similarly, we have an, let me just write it out, I guess. So similarly, there exists delta 2 bigger than 0, so that now I'm using this piece. So that x minus c less than delta 2 implies f of x minus L2 is going to be less than epsilon over 2. Okay? And so then we're going to choose delta to be the minimum of delta 1 and delta 2, so that x minus c being less than delta implies that x minus c is going to be less than both of these, since delta is the minimum. All right. And so if I look at L1 minus L2, I'm trying to make this arbitrarily small. I'm trying to deduce that L1 equals L2. So I'm trying to make this distance between L1 and 2 arbitrarily small. So I can use some sorcery from the triangle inequality, and you guys have seen these tricks in previous lectures and in your homework and stuff. But, you know, if I do this sorcery here, I notice that I have an f of x minus L1 and an f of x minus L2. And so what I can do here is I can write this in a sneaky way as L1 minus f of x plus f of x minus L2. Okay, because that's just L1 minus L2, those middle terms cancel. And by the triangle inequality, this is going to be less than or equal to L1 minus fx plus fx minus L2. And this is the same thing as fx minus L1. If you just factor out a negative sign by properties of absolute value, this guy equals this guy. So that's what I did there. And then we know that this is less than epsilon over 2 because we have this hypothesis is satisfied. And we know that this is less than epsilon over 2 because this hypothesis is satisfied. So this is less than epsilon over 2 plus epsilon over 2, which equals epsilon. And, you know, so we have L1 minus L2 is less than epsilon. And so epsilon is arbitrary. Epsilon is just a number bigger than 0. It can be anything. So we can let epsilon go to 0 from the right. And this gives us that L1 is equal to L2. Okay, so that's the idea here. So if we have a limit, there's only one limit. Limits are unique for functions. All right, so our next theorem is pretty handy. It's a sequential criteria for limits. And so we're going to assume that we have a subset of the real numbers a, and we have a function from a to r, and that c is a limit point of a. So just the usual assumptions that we make for limits. Then we have an if and only if statement. We have the limit as x approaches c of f of x is L, if and only if for every sequence a sub n, for which for all n is not equal to c. Okay, so it's c is a limit point, and a sub n converges to c, we have that f of a sub n converges to L. Okay, so yeah, so this is an if and only statement, so we have to prove the forward direction and then the backward direction. So let's go ahead and do that. So for the forward direction, what is our assumption? We're assuming that the limit of f of x is going to be L as x approaches c. So assume that the limit x approaches c of f of x is equal to L. All right, so since that's true, we let epsilon be bigger than 0. Then, by the definition of the limit, there exists a delta bigger than 0, so that x minus c less than delta is going to imply that f of x minus L is going to be less than epsilon. All right, so I'm just going to highlight this. Okay, and what are we trying to prove? We're trying to prove that this implies that whenever we have a sequence converging to C, then f of that sequence converges to L. That's what we're trying to show. So let's just say we have a sequence converging to C, and like this is our ultimate goal right here. We're trying to show that. So suppose let's see. Oh, I'm looking at my notes. I think I have a typo. So in the notes it says since a sub n converges to 0, it should say a sub n converges to c. Sorry about that. So suppose a sub n converges to c. Well, what does that mean? What does it mean for a sequence to converge to a number? That means by definition of sequences converging, then there exists some n in the naturals. So that when you go far enough out in your sequence, when n is bigger than capital N, this implies that a sub n minus c is going to be less than, well, usually less than epsilon, but we need this. Remember, we can choose epsilon to be anything we want. So in order for the proof to work, we want to choose this to be less than delta, right? Because delta is a positive number bigger than 0. So we're like using this in replacement of our epsilon. Okay, so by the green portion above, what does this imply? Well, it says that a sub n minus c is in the delta neighborhood. So then this applies, right? This applies. Then okay, we're just using the green portion that we know is true. We know that a sub n is bigger than c, so there's some capital N, so that this guy is in the delta neighborhood. And then by the green portion, this implies that this is going to be in the epsilon neighborhood. Okay, so we have one direction. So for the other direction, we're going to proceed by contradiction. So we're going to suppose that a sub n converges to c implies, so we're doing the backwards direction. We're assuming the predicate of the sentence, if you will. I haven't used that word in a long time. Shout out Miss Cochran, 7th grade English teacher. Is that right? Predicate? subject, predicate. Okay, but I think you guys know what I'm saying. It's like the second part of the statement. We assume that. So assume this is true. And for the sake of contradiction, we're going to assume that the limit as x approaches c of f of x is not equal to L. Okay? So for the sake of contradiction, assume that the limit as x approaches c of f of x is not equal to L. Okay. All right, well, by I think the third slide, we said what this means formally. Okay, we said what it means for the limit to not be L. We said that then there exists, so we're just negating the statement of what it means for the limit to exist. And so to negate that for all epsilon there exists a delta, we're going to say that there exists a delta, an epsilon bigger than 0, such that for all delta bigger than 0, there's an x in the neighborhood. There is an x such that when it's in the neighborhood, x minus c being in the neighborhood implies that f of x minus the limit is going to be not less than epsilon, we're negating it, bigger than or equal to epsilon. Okay, so this is just what we talked about a few slides ago with that piecewise function. When the limit doesn't exist, we have this statement. Okay, so consider this is a sequence. Delta n equals 1 over n. All right, so what does my hypothesis say? Okay, so it says that suppose that a sub n converges to c. This implies that f of a sub n converges to L. Okay, so this is a neighborhood I'm choosing, this delta n. So then there is some xn, so that xn minus c less than delta n. Remember, this piece right here is saying that for any delta neighborhood, so I'm choosing my delta neighborhood to be dependent on n. Okay, there's some xn so that xn minus c less than delta n implies that f of xn minus L is going to be bigger than or equal to epsilon. And so we have xn minus c, just by definition of delta n, we have that this is going to be less than 1 over n. And what does this mean? You know, you can think of it kind of informally here. When n gets really, really big, this sequence, I mean, this is going to be less than 0, right? And so you can think that, you know, just like we did with the L1 minus L2, making epsilon arbitrarily close to 0, it's the same thing here. If we let n get really large, this sequence is converging to 0. And so the big idea here is that we have our sequence xn goes to c because of this, right? When n gets large, this thing goes to c. Okay, so this is a problem, right? Because we have a sequence that converges to c, and by by our hypothesis, whenever we have a sequence converging to c, f of that sequence better converge to L. But that's the issue, right? We have f of x n does not converge to L, right? Because it's bigger than or equal to epsilon. It should be less than epsilon. So this is a contradiction. And therefore, the limit does exist, and it equals L. Okay, and so that's the end of the proof. So we did the forward and the backward direction, and it's shown. Okay, so this is kind of useful because the idea here is like, all right, if you have a sequence converging to C and you have some other sequence converging to C, but when you do f of the first sequence, it converges to some limit L1, f of the second sequence converges to L2, then by this criteria, the limit can't exist because it's an if and only if sequence, right? So, and limits are unique, right? So we can't have that, you know, this guy goes to L1 and L2. So we can utilize this with this example. So it says, use the sequential criteria for limits to show that the limit as x approaches 0 of sine of 1 over x does not exist. So this is kind of cool. All right, so we're going to find two sequences that go to the same c. In this case, our c is 0. And we're going to show that f of these sequences go to different things and therefore deduce that the limit can't exist. Okay, so consider the sequence a sub n equals 1 over n pi. Now as n gets large, this thing is going to go to 0. We don't need justification for that. We've seen a million times that 1 over n goes to 0. So 1 over any multiple of n is going to go to 0 as well. And also consider this sequence, b sub n equals 1 over pi over 2 plus 2 pi n. Okay, this also goes to 0. I mean, just think about it. If n gets really large, the denominator gets really large. And when the denominator gets really large and the top is fixed, well, that goes to 0. Okay, so both of these go to 0. And our sequential criteria says that for any sequence going to 0, when we plug f of that sequence in, it should go to a common limit. Okay, and if it doesn't, then the limit doesn't exist because limits are unique. Okay, so let's check it out. Let's check out f of an. I'm just plugging in an in for f, which is sine of 1 over x. Okay, so this is going to be sine of 1 over an. And just by what an is, this is sine of 1 over n pi. And that's just equal to sine of n pi. Now, in any case, this is going to go to 0 because it doesn't matter whether n is even or odd. Sine of n pi is always 0. So this guy goes to 0. So f of an goes to 0. But if we look at f of bn, that's going to be sine 1 over bn equals sine of 1 over pi over 2 plus 2 pi n. So that's just equal to sine of pi over 2 plus 2 pi n. And so this is always going to be, if you remember the trig terms, coterminal to pi over 2, right? Because whatever n is, it doesn't matter. We're always going to get an even multiple of pi. And so like you can think, here's pi over 2. This is if n equals 0, we're at pi over 2. If n equals 1, I just add a rotation. I'm still here, add a rotation. I'm still here, etc. You guys know how this goes. So the sign at pi over 2, or any multiple, any even multiple of 2 pi plus pi over 2, is going to be 1. Okay, so this goes to 1, And so f of b sub n goes to 1. Well, that's a problem, right? We have that both a sub n and b sub n go to 0, but we've found that when we plug in a sub n into f, it goes to 0, but when we plug in b sub n into f, it goes to 1, and therefore the limit can't exist by the sequential criteria. It has to go to the same thing. But if they go to different things, the limit cannot possibly exist because limits are unique. Okay? All right, so I'm just going to go through this pretty quickly because we've seen this in other contexts with sequences. This theorem is a direct consequence of the sequential criteria because we already have the limit laws for sequences. And so by the sequential criteria, this is going to be true as well. Okay, so we're not going to justify this, but basically it's everything you think will be true if you have the limit of some function as x approaches c equaling L, and the limit of another function equaling m as x approaches c, then these limit laws hold. So if you have a scalar multiple, you're multiplying it by f of x and then taking the limit. That's the same thing as multiplying the scalar by the limit, and so forth and so forth. When you take the limit of sums, you just add those limits. Same thing with multiplication, you just multiply the limits. With division, we want to make sure that g of x is never going to be 0 for that to work, and that if your limit of g of x is equal to 0, then this isn't going to hold either. So you have to make sure the limit is not 0 so that this isn't undefined and that g of x is not 0, and then the division will hold. So that's that. Okay, so a corollary of these limit laws and the sequential criteria is going to be the squeeze theorem for functional limits. Now, we already talked about the squeeze theorem for sequences, so the functional limits piece is just going to follow directly from the sequence piece and the sequential criteria. Okay, so let me just state it and do an example. So if we have functions f, g, and h, and we are supposing that g of x is sandwiched or squeezed between f of x and h of x, we're going to assume that f of x is going to go to L, okay, so that outer leftmost function is going to go to L, and we're also going to assume that the rightmost function goes to L. And so by the squeeze theorem, if these outer things go to the limit, then that's going to tell us this inner thing is going to go to the limit. Okay, so let's put this in practice with an example. Okay, so we're going to suppose that f of x equals this when x is not 0, and that this function is defined to be 0 when x does equal 0. Now, we don't care about the piece where f of x equals 0 when x is 0 because we're talking about limits here, okay? And if x is approaching 0, I don't care what happens when x equals 0. So we're going to kind of like neglect that piece for now, okay? So we want to prove that this thing equals 0, and we're going to notice that sine is always going to be squeezed between -1 and 1, right? Sine of any angle, in particular 1 over x, is going to be bigger than or equal to -1 and less than or equal to 1. And so if I want it to look like this, I just multiply everybody by x squared. And so I get x squared sine of 1 over x is going to be between -x squared and positive x squared. Okay, and by the squeeze theorem, this thing is going to go to 0 as x approaches 0, and we're not going to justify that now, but it's just limit laws. You know, you can plug in 0 because it's polynomial, and this also goes to 0 as x goes to 0. And therefore, by the squeeze theorem, that middle portion has to go to 0 as x goes to 0. So by the squeeze theorem, we have that the limit as x goes to 0 of x squared sine of 1 over x does equal 0 as well. Okay, so that's the squeeze theorem. Okay, so the last topic of conversation in this lecture is going to be continuous functions. And the definition for continuity looks very similar to definition of limits, because essentially that's what we're doing, but there's some slight differences that I'm going to highlight in a bit. So here's the definition of a function being continuous at a point, C. Okay, so a function is continuous from A to R at a point C in A. Okay, so here's the first difference, is that now we're requiring our function f to be defined at C. If it's not, whereas with the limit we didn't care. Like, who cares if f is defined at C because we're just looking at limits. But here with continuity, we actually want the point C to be defined on f. Okay, so that's the first difference here. If for all epsilon bigger than 0, there is a delta bigger than 0, so that for all x and a, where x is in that delta neighborhood, now notice that I don't have the stipulation that this is going to be bigger than 0. This could be equal to 0. We could have x equals c, and it's still going to work. But I'm just going to shorten it and write this guy for now. So that whenever we're in the delta neighborhood of c, this implies that f of x minus f of c is going to be less than epsilon. Okay? So in other words, I mean, we're just replacing f of c with our limit L here. In other words, f of x is continuous at c if the limit as x approaches c of f of x is equal to f of c. So we're just seeing this is in replacement of our limit L. Okay, and we can see a picture here of this continuous function. We're looking to see if it's continuous at c. So if I give you an epsilon neighborhood of f of c, are you able to produce a delta neighborhood so that this guy is true? Okay, so very, very similar to the definition of limit of a function. So let's do some examples where we're proving that a function is continuous. So the first example, we have a function from the reals to the reals given by f of x equals x, just your friendly line f of x equals x, and there's no restrictions in our domain here. We can plug in any real number we want, no problem. And we want to prove that f is continuous on the reals. So for any point c and r, our definition holds. Okay, so let's go ahead and prove this. Well, maybe we'll do Scratch first. So it's going to be the same kind of spirit as the functional limits and the sequential limits. So what are we trying to show? We're trying to show that x minus c being less than delta is going to imply that f of x minus f of c is going to be less than epsilon. And so if I start from this point of view here, if I just plug in f of x equals x and f of c is equal to c, right? Then I can simplify this a bit more to x minus c is less than epsilon. So what should I choose my delta to be so that this implies this is true? Well, how about epsilon, right? That's going to work. So let's do that. So here's our proof. So our proof. Let epsilon be given. And suppose that c is in the reals. We're going to choose our delta to be whatever epsilon you give me. Then our hypothesis, x minus c less than delta is going to imply, well, delta was epsilon. X minus c is going to be less than epsilon, which implies that f of x, right, it's just definition, f of x is x, f of c is c. F of x minus f of c is going to be less than epsilon, okay? We have everything now. So therefore, by the definition of continuity, f of x is continuous for all c and r, or at all c, maybe. It's a better way of writing that. Okay. Let's do another one. So this time I claim that, oh wow, I didn't define f. That's embarrassing. Did I do it in the notes? Oh, Jesus. Oh my gosh. What is wrong with me today? Okay, well, whatever. Let's define f. F of x is equal to square root of x. Okay, I didn't put that in the notes, so go ahead and add that. And so we are considering inputting values. Okay, this is our domain here. We're inputting things that are positive or 0. Okay, we don't want to ever put a negative number in the absolute value. I'm sorry, in the square root. So that's what our set is, and we claim that f is continuous on A. So wherever x is bigger than or equal to 0, we know that f of x is continuous, and we know this from our experiences in life that this is true. But let's prove that it's true. So here's root x, and a is just these x values. We don't care about x is less than 0. All right, so let's do some scratch work to see how to do this. So what do we want? We want, for all epsilon bigger than 0, that there exists a delta bigger than 0, so that x minus c less than delta is going to imply that f of x minus f of c is going to be less than epsilon. That's what we want. So again, we're going to start backwards and see if we can figure out what delta needs to be. Okay, so we have f of x minus f of c. Well, f of x is root x and f of c is root c. So this is just root x minus root c. And there's not a lot we can do here. If we say this is less than epsilon, we, there's not a lot we can do. We really would love to get rid of the square roots. And so we use that trick that we teach our algebra students of multiplying by 1 and via conjugation. Okay, so we're going to multiply by the conjugate to make this a little bit more wieldy, I guess. So if we multiply by 1 or conjugate, so this is going to be this over this. Okay, and so I'm not going to, show all of the steps here because I think we all know how to conjugate stuff. But, well, whatever. I guess I will. So if we just do root x minus root c times root x plus c in the absolute value, and we're dividing by root x plus root c. Okay, so the top, what's going to happen to the top? Well, the middle terms are going to cancel, and I'm just going to be left with x minus c on top, which is cool because look at that. That's where I'm headed. That's where I want to be. And then on bottom, well, so I'm taking the absolute value of something completely positive. Square root of x plus square root of c is going to be completely positive, so the absolute value bars are not necessary, so I can dump them. So this is just going to be root x plus root c. And I want this less than epsilon. Let's get rid of the root x because remember, I don't want to choose delta to depend on x, so let's bound it. Okay, so the bounding here is I know that this whole thing, since root x is positive or 0, this is going to be less than or equal to x minus c over root c. Okay, and now I'm in a good position because delta can depend on c. That's not a problem. We just can't have delta depending on x. But notice that this is only valid when c isn't 0. If c equals 0, we have to take care of that case separately. Okay, so this is the case where c is not equal to 0. Okay, and c again is in A, so it's gonna be positive if c is not equal to 0. All right, cool. So that was a little note there, and I'm gonna erase it to make room. We want this less than epsilon, so solving for the x minus c, we get this is less than epsilon over root c. So that's, I meant times. So this is going to be epsilon times root c. And so this is what I should choose my delta to be in the case where c is not 0. So this, in case where c is not 0. Now when c equals 0, we have to deal with this differently. So when c equals 0, I want this to imply the blue box. So when c equals 0, I have x minus 0, right? Okay, so let's just plug in when c is 0 into the definition. I want x minus 0 to imply that f of x minus f of 0 is less than epsilon. Well, or I want this less than delta to imply that this is less than epsilon. So f of x, so this is just saying x less than delta. I want this to imply this guy is less than epsilon. And so this is going to give us root x less than epsilon. Absolute value of something positive, we can remove the absolute value bars to just give us this is less than epsilon. Okay, so let's see. Okay, so if I isolate x here, because I can drop the absolute value bars here since x is positive. This is going to give me x is less than delta. We want this to imply that f of x minus 0 is less than epsilon. So if I square both sides down here, I get x is less than epsilon squared. So it suffices to pick delta as epsilon squared. So in that case, we chose delta was epsilon times root c. When c is 0, choose delta equal epsilon squared. Okay, so we have two cases to do. All right, so let's do it. Let's write the proof out. I'll be fairly brief with this since we already did the scratch work. Okay. All right, so here's the proof. Let epsilon be bigger than 0 be given. Okay. When c equals 0, so this was the second case that we proved, choose delta equal to epsilon squared. Then x minus 0 less than delta implies square root of x minus square root of 0 is less than epsilon, and that's just by our scratch work. So it's continuous at 0. When c is bigger than 0, choose delta equals epsilon root c by our scratch work. Then x minus c less than delta is going to imply that x minus c is less than epsilon over root c. And by our scratch work, this is going to imply that f of x minus f of c is going to be less than epsilon. So for all c bigger than or equal to 0, this implies that f of x is continuous at c. Okay, and that's pretty much it. So I hope you guys enjoyed the video, and I'll see you guys next time. Thanks for watching.